we're told that this series converges to a function y such that it solves this differential equation. And then they give us some initial value information. So what we could first say is that y is the sum from n equals 0 to infinity of a sub n x to the nth power, which means, if we look at some terms in that series, that's going to be a sub 0 times x to the 0 power plus a sub 1 times x to the first power plus a sub 2 times x to the second. And I'm listing a few because we're going to want something to look at when we look at the derivative of y. Okay, and actually, let's see, is this a good place if we plug in 0, 0. Yeah, so now we can start finding out what some of these values are for a sub 0, a sub 1, a sub 2. If you plug in 0 in for x, it says we get out 0 for y. So that means if we plug in a 0 in for y and a 0 in for x, well here, this is x to the 0 power, right? So anything in here is just going to be 1. So we're not going to plug in 0 here because we could, it would just be raised to the 0 power, so that'd make it 1. But this is going to be a sub 1 times 0 plus a sub 2 times 0 squared plus, and it keeps going. So this equation is solvable because every term other than the first term is being multiplied by 0. We found out that a sub 0 equals 0. And now let's look at the first derivative. With the first derivative, what we're doing is we could differentiate term by term. That was one of the tools that we learned in this section. So if you differentiate, this is x to the 0, that's getting kind of distracting, that's just 1, right? So if you differentiate this with respect to x, that's a constant, so that's 0, right? And if you differentiate this with respect to x, it's just a sub 1. If you differentiate this with respect to x, that's 2a sub 2 times x. And differentiating this term, that's going to be 3a sub 3 x to the second, and then maybe one more for good measure, 4a sub 4 x to the third, if we kept those terms going. So that's the first derivative, and we could do the same thing. Plug in the initial value information. Maybe we can find out what a sub 1 is, because it says if you plug in 0 everywhere for an x, you should get out 1 for the derivative. And the same thing's going to happen. I think you can see this is going to be 0, this is going to be 0. So the whole thing means that a sub 1 equals 1 in this case, because everything else becomes nothing. So we found out a sub 0 is 0, a sub 1 is 1. We can, let's see, we have to involve the second derivative because of the differential equation they gave us. The second derivative is subtracted by 2 times the first derivative. So we've got to figure out what the second derivative is. And so again, that's just looking up here, differentiating term by term. Derivative of this with respect to x is 0. Derivative of this with respect to x is 2 times a sub 2. Derivative of this with respect to x is going to be 6a to the third x to the first power. Derivative of this is going to be 12. 12a to the fourth x to the second, and that might be enough. Now we have something we can plug in. We can plug this into the differential equation. We can plug this into the differential equation. And what do we have for y? We have this that we can plug in for y, all into this equation up here, okay? So probably easiest if I pause and I'll plug all those in. So I've got everything plugged in, and I actually started putting some initial value information in. We had that a sub 1 was 1. That's why you see, wrong color. A sub 1 was 1, so we can plug in a plain old number there. A sub 0 was 0, so I crossed that out, but here, let me back that up. This is what it looked like. All equals 0. And so we plugged in, it's like you're plugging in a 0 for a sub 0, so we can just scratch that out. And we also found that a sub 1 was 1, so we can plug that back in. And so now, remember, the goal is, this is an equation that we have to solve, right? We got to figure out what certain values are in this differential equations that, actually it's not a differential equation anymore. And we got to find out the values for like a sub 2 or a sub 3 that are going to help us solve this equation. So right now, the best bet is to try to group the terms in terms of x, because when we're trying to find a solution to the equation, we need to figure out values for like a sub 2 to find out what it's going to make, what it's going to take to make everything equal 0. So let's start with actually the plain terms that don't have that don't have x, and I think the only one we have here is -2 times 1 makes -2. So I've taken care of that. I'm going to cross it out so I don't reuse it. Let's see, now we're up to x to the first. Oh, sorry, this is a plain old constant too. This does not involve x, so we'll add that here. Plus 2a sub 2. And now x to the first power, that's what we're interested in next. Oh, and sorry, real quick, the -2 in front of y prime, I put a parentheses because I'm distributing a negative number into everything on the inside, so that parentheses is important. But we have 6a to the third, a sub third x, a sub 3x. So we'll start writing out all the terms that have x to the first power. So that's -2 times 2 makes -4, a sub 2x. So we got that taken care of. We got 1x. So we can cross that out. And then we can start working on terms that would make start putting out the x squared terms here. But maybe we can stop here. We can find out what a sub 2 is, and then we'll be able to figure out what the solution is to this big log problem, right? This whole thing is supposed to equal 0. So if this whole thing is going to equal 0, then we know that the Planel numbers have to combine, because they're the only like terms with one another, right? They have to combine to make 0. So that tells us that a sub 2 is going to be 1, right? That way -2 plus 2 makes 0. There's no other like terms that can combine with these ones based on what we were looking at, so we know those have to disappear and become 0. You can use the same type of logic here. Everything has to cancel out. These are the only like terms because these are the only terms that have x in them. So we need the 6a to the third plus a -4a to the second. I'm saying to the second power, sorry. 6a sub 3 subtracted by 4a sub 2 plus 1. That also needs to equal 0. And then we just found out what a sub 2 is. Now we have a quick little equation we can solve. This is 6a to the third minus 3 equals 0. So we're going to get that a sub 3. I said to the third again, man. A sub 3 is 1/2 when you solve that equation. And then you can do the same thing with your x squared terms. Keep going up the powers like that. If you were to list out the x squared terms, it's 12a sub 4 x squared plus, now this is -2 times 3, so that's -6a sub 3 x squared plus a squared x squared. Those also have to equal, the coefficients have to equal 0 because those are the only like terms of this type of x squared. So it has to be true that 12a to the fourth subtract 6a to the third plus a squared equals 0. And so if you plug in the information we've already gathered, that a sub 2 is 1/2, and that, oh no, sorry, a sub 2 is 1, and then a sub 3 is 1/2, so that's going to be -3 when you plug that in. Now we can solve the equation for a sub 4. And you can keep working your way backwards. You can now start, you'd have to expand this blue one a little bit more to find out, looks like we're going to be getting a sub 5 next. Okay. I guess I'm jumping ahead of myself here a bit because this is -2 plus 2. So this is a sub 4 would be 1/6. And then a sub 5, let me see if I can work backwards here. This is 6a to the third minus plus 12. What was happening? It was y, the second derivative of y. I went back in the notes. This would be 20a to the fifth x to to the third? I wrote down to the fourth, but I think it's supposed to be the third based on the powers here. So for the second derivative of y, another term is 20 a to the fifth x to the third. Okay, and I think we got what we need to make one more little equation. If you take all the terms that are x to the third, they have to have coefficients so that they cancel out so that it can equal 0. So we got this. Oh, sorry, that one is, we forgot to distribute the -2. -2 times 4 makes -8 a to the fourth x to the third. And then our x to the third term over here is just plus a to the third x to the third. So in order for that to be sorry, we don't want that equals 0, but in order for our whole equation to equal 0, those leading coefficients need to combine to make 0. And we already know what a sub 4 is. That's 1/6. We know a sub 3 is 1/2. Oops. Just look at the coefficients. So now we have something to solve for a sub 5. Got some fraction work going on. Let me see how quickly I can do that. This is 3/6. So it's going to make -5, 6. 5, 6. So this is going to be equal to 5, 6. And multiply both sides by 1/20. This cross cancel. Makes 1/24. So there's our fifth term. A to the a sub 5 is 1/24. That's just what we needed for that list. And I think we lost it. It was previous in the notes, but a sub 1. We plugged in our initial value information. We got 1. So there's our list. Let's look at what y is now that we have the first 5 coefficients, because now hopefully we can detect the pattern. So the goal of the problem is a little bit different than the goal of the problem we did in the lecture video. In the lecture video we tried to find y equals something, come up with that function. And since we have those coefficients written off to the side, you could write out those coefficients and eventually you could see a pattern forming. But this question asks us up here to relate the current term and the next term and then the next term after that to one another. And we were actually doing that in the steps when we were trying to find each value, a sub 1, a sub 2, a sub 3, etc. Okay, we were doing that. We were finding the next term. Let's just go over one of those and maybe that can help us determine the pattern that we need. Let's see, when we related the x's to each other, we said 6a sub 3 minus 4a sub 2 plus, and then this was our a sub 1, right? So we could say a sub 1, that needed to equal 0. That was one of the equations that we solved. Okay, and then if we looked at the x squared equations, actually we still have it written over here, the bottom right portion of the screen. That equation was 12a to the fourth minus, not a to the fourth, a sub 4, minus 6a sub 3 plus a sub 2 needed to equal 0. And maybe one more for good measure. When we did the x third powers, we had 20, looking up here, that's 20a to the fifth, and x, so we did minus 8a to the fourth, and then plus a to the third, a sub 3 equals 0. So there's a pattern forming here. We're trying to relate a sub n, so like this part here could be like our a sub n, because this is like this is the lowest term in when we're trying to solve each of these equations. It's a sub 1, and then the next one, this is like our a sub n plus 1, because it's always one above this base one, so this is like a sub n plus 1. Let's see, that was always, I need it in terms of an n though. Multiplying by 2 each time, that shouldn't be too hard to work with. I might have to come back. So this one would be a sub n plus 2 and then multiply by 2. That's adding 6, adding 8. Okay, I think I got it. So let's in this case, this is like when n equals 1, right? So a sub n would be a sub 1 in that case. This is like our general formula that we're trying to get it to. This column, we're always adding a sub n, a sub 1 plus a, and then and the next time we solved an equation, we were trying to solve a sub 2. And the next time we were trying to solve the equation, we're trying to solve a sub 3. So when n was 1, then we found the coefficient was -4 in front of a sub n plus 1. When n was 2, coefficient was -6. So it's like it's minus 2 times n plus 1. Because when n was 1, 1 plus 1 made 2, and 2 times -2 made -4. When n was 2, then we add 2 plus 1 makes 3. 3 times -2 makes -6. When n was 3, yeah, that formula still holds because if you plug 3 in here, 3 plus 1 makes 4. 4 times -2 makes -8, just like it's supposed to. So we've got the coefficient for this part done. Now we need this coefficient out here. 6, 12, 20. That one's not as constant. Maybe 2 times 1 would make 2. 3 times 2 would make 6. What if we did n plus 1 times n plus 2? If we have n plus 1 times n plus 2, then when n equals 1, that'd be 2 times 3 makes 6, just like we wanted. When n equals 2, then be 3 times 4, which makes 12. Okay, so I think that's it. We have to have n plus 1 and n plus 2 as a coefficient in front of this term. Okay, so that's an equation that relates a sub n plus 1, and a sub n plus 2. So this is a particularly challenging problem. I think it shows up near the end of the textbook. So for anyone watching this video, because they got stuck on that last part, you're not going to have to do this on an exam. I think that's going above and beyond the calculus part. That's kind of tricky. That's asking you to go back over your work and find a pattern within your pattern. What's really important is that we want students to at least know that when you are trying to solve a differential equation, you can convert y to a series, and then you can differentiate term by term to solve, because that technique can help you solve differential equations that otherwise you wouldn't have any other tools for. So the big picture for this class is that you want to be able to know how to come up with these coefficients, and then like we saw in the video this week in the lecture, you want to be able to find out what that solution is, and that would be when you go back in and you plug in a sub 1, that'd be x to the first, plus a sub 2, which I think is x squared, plus a sub 3, that's 1/2 x to the third. You would want to be able to know how to convert that. Using the power series, you want to be able to convert that to some sort of function. Okay. Yeah, this is demonstrating that you know how to find those coefficients. That's demonstrating you know how to break it up into a series. So that's the important part. This part down here is just kind of a tricky question to add on top of everything else.